Okay, this is a standard titration problem. We are adding a strong acid to a weak base solution. We are given the volume and the molarity of the strong acid, hydrochloric acid, and we are given the volume and the molarity of ammonia, the weak base. Also, we are given Kb of ammonia. So what do we do now? So there are several solutions to this question, and I'm going to show the first one is a standard solution. I think it's slow and clumsy, and if we're on exam, it would take a lot of time. So I'm going to show this first standard solution. So first of all, we need to use a stoichiometric chemistry, then we use I-stable, and we solve a quadratic formula to get the result. If the Kb or Ka is large or small, very, very small, very, very large, we can shorten the time we spend on the quadratic formula. But first step is stoichiometric chemistry. Second step is I-stable. So let's go. So we'll calculate the mole when we want to do stoichiometric chemistry. We found the mole of hydrochloric acid is 0.00505, and ammonia is 0.0104. So I wrote the reaction formula over here, and we can see that ammonia is in excess. It's more than strong acid, hydrochloric acid. So all hydrochloric acid will react with ammonia. So, and in our actual reaction, we used up 0.00505 ammonia and used up all the hydrochloric acid, and we produced 0.00505 because all the coefficients numbers is 1. Therefore, they create the same amount of in terms of mole. Our conjugate acid of ammonia and also the chloride ion, and you can see 0.00505. All of them are 0.00505 mole, and then because we initially have a 0.0104 mole, and we use that mole to minus we used up ammonia, the total ammonia mole before we add a strong acid, hydrochloric acid, and that's the used up ammonia. Finally, we got, this is stoichiometric chemistry, we got a 0.00535 mole of ammonia, and then we created conjugate acid of ammonia 0.00505. These two species that gonna control the final pH. Our goal is to get a final pH. So second step, we need the molarity for each species, because we just finished the stoichiometric chemistry, we're going into the I-stable. So we need to know the total volume in order to calculate the molarity for each. So the total volume is 0.0365 liter. Okay, and then we calculate the ammonia molarity, and then we calculate its conjugate acid molarity, and we put in the I-stable. So this is a reaction after we used a strong acid to react with ammonia. There's no strong acid in it. It's only ammonia and its conjugate acid in it. So the reaction equation gonna be like this one, and then our I-stable will be like this. And we'll have another species if you look at OH. OH is also determining the pH of the final solution. So I'm gonna add OH here, and originally it has assume that it has 0 there. We added X, so the OH is X. But why the ammonia's conjugate acid has a starting molarity? This is because our reaction, ammonia and hydrochloric acid, created this conjugate acid. You see, that's its mole, and we calculate the molarity here. And so we have initial starting molarity already for our conjugate acid because of the above reaction. So the conjugate acid of ammonia does not start with 0. It starts with a starting molarity that's we calculated, and then the OH is 0. And the OH increased by X, and the conjugate acid increased also by X because all the coefficients is 1 here. So 1X mole of molarity of ammonia will create a 1 molarity of its conjugate base, and also 1 molarity of hydrochloric acid. I mean, also the hydroxide acid. Oh, sorry. So now what we do is Kb. Remember, we're creating the hydroxide ion, so we're gonna be Kb. Kb is equal to so what is the products? Products you're gonna put on the numerator and side, and put the place and the denominator for the reactant. So reactant is water is liquid, so it still has a 1 here, and we can use our 0.147 minus X at the bottom. And then let me change to another color, and we have conjugate acid 0.138 plus X multiplies the other species as product. So that's what we got here. So again, if we do this work, remember this equal to already given 1.8 multiplies 10 to the negative 5. So this is going to be a quadratic equation, and we assume x is very small. Okay, so we can use 0.138 multiplies x and divide 0.147 and equal to our kb, which is the same 1.8 multiplies 10 to the negative 5. Then we get x equal to, like approximate, let me show it here, approximate. And once we know x, we know the POH, and once we know POH, we know the pH. That's it to solve the problem. So we need to use 0.147 multiplies 1.8 multiplies 10 to the negative 5. Right here, I'm using this calculator. That's the first number. Then we need to divide it 0.138. So 0.138. So that will be 1.92 multiplies 10 to the negative 5. 1.92 multiplies 10 to the negative 5. If you compare this number with our calculated molarity, starting molarity, initial molarity here, and you can see they have a significant difference. So x is significantly smaller than our starting initial molarity. Therefore, the approximation assumption as x is small is valid. Therefore, can go on use this one. Now we can calculate POH equal to negative log and this x we calculated, which equal to approximate to. So just to do this, answer in 4.72. So 4.72. But remember, this is POH. We want a pH. At 25 Celsius, 14 minus POH is equal to pH. So we're going to have a 9.28 as the final result of the pH. Then we solve this problem. That's the first method. So I'm going to show the second method. Use the small space on top, just to indicate how fast the second method is. So, all right, second method, we still use molarity stoichiochemistry, but this time we make it so fast. We have an equation here, so we put a kb here, and then we plus log, and this time because our base and the conjugate acid stay the same solution, we don't have to calculate their molarity for each. We just need their moles after the reaction with HCl, and then we assume the x is small at the same time. And once we calculate pH, we can validate it whether it's small or not. Let's go. So again, we have we just show the first part of this. So we have a strong acid as 0.00505. We added this much, and the original stock and NH3 is this many mole, 0.0104. So what's the result? How much reacted stoichiochemistry based on? And NH3 actually got, we can get this number right here, 0.00535. So 0.00535. This is for the place denominator we put in the base. And remember, we use log kb, so denominator must be a base. And the numerator is going to conjugate acid. So how much conjugate acid we created? 505. All right. Same mole we use for the strong acid. And acid is the limited agent, reactant. So that's it, and we can calculate the final pH. Let's do a calculation. So I'm going to put my calculator here just to show you how advanced this method is. So log and negative log. We got a 1.8 multiplies 10 to the negative 5. Right? And plus log 0.00505. Right? Divide 0.00535. So in order to see everything, I'm going to do this so that you can see better. 0.003535. Okay, so I can let you see everything here. So I have calculated this must equal to the POH. Okay, this result must be equal to POH. Let's calculate. So POH is 4.72. I'm sorry, I need to change this one because we're using kb, and also the base is at the denominator's place, and its conjugate acid is on the denominator place. So POH is equal to 4.72. So what's its pH? Just to do a mental calculation, it's going to be 9.28. So we got a 9.28. Like how much time we spent? Like less than a minute. And then this is pH we calculated using second method, this formula. And look at the pH we calculated at the bottom, 9.28, same number you see here. And you spend all this time calculating the mole. After that, we calculate mole for the second method too because we need a mole to put here. But we don't want to do an ice table and then do a quadratic formula, then calculating X. And then write this equation and put out this ice table. So we save a time to make an ice table. Also this thinking all of here. And also you can calculate the pOH, pH. We do that too, pOH. But our pOH, the pOH here calculated based on X. But at the top, the second method, pOH, it's based on this formula. And right away we got 4.72 as pOH, then pH 9.28. Assuming that you're on an exam, how much time you have saved for doing this? All you have to do the stoichiometry, like I did for the first method, and then use the formula. So, and now, the one last step, you need to verify the X is small. How do you do that? So the X I'm talking about is X. What is X? X is molarity of OH. Okay, molarity of OH. So I'm not talking about the X, and that is molarity of the hydronium ion. Let's do OH. So how do we calculate the X? We use pOH, don't use pH, because this OH hydroxide ion. So what we do is like we do the 10 to the negative pOH 4.72, which equal to, as I show here, 1.91 to the negative 5. So then 1.91, like it's an approximate number, 91 negative 5. And this number compared with our molarity of our NH3. Okay, NH3, how much we calculated? 0.00535. And that's the mole left. And our total volume is what? 0.0365. We calculate over here. Yeah, you're going to say that we still need to calculate the total volume into one of the reactants. We'll do the reactant base and molarity. But you can roughly say that you have this mole, this kind of mole, and you have negative 5. Basically, it's a small x. Therefore, this equation is valid. You can use this one equation. This equation also depending on X is very small compared with starting base. So the result is, we already calculated here, right here, 0.147 molarity. Okay, so use this number, divide that number, it's less than 5%, less than 5%. I can calculate it for you right here. So it's a 1.91 multiplies 10 to the negative 5 and divided 0.147. And that's your final. And the multiplies 100. Yeah, it's 0.1213%. 0.1013%, much less than 0.5. Therefore, you can use that formula. So you just need to validate that X is small enough. I mean, the concentration of the OH hydroxide ion is so little that you can use this formula. So the method 2 is much faster than the method 1, a traditional method, as we say here. So this is the trick and the tip for solving standard titration problems so fast. Different two volumes, and you need to have total volume. Then you do ice table. The ice table going to take a lot of your time. Instead of doing ice table, go for this route. Negative log and KB, and plus log, and the denominator going to be the base, and denominator going to be the acid. If you're doing a strong base, titrate a weak acid, what do you do? Negative log Ka multiplies log, and the bottom going to be your acid, weak acid molarity or mole. I mean, we're using mole because they're the same solution. So you use molarity, you use mole the same. But your denominator gonna be, this time, if you use Ka, gonna be the conjugate base that you created based on your strong base. So this works with strong acid, weak base, strong base, weak acid. So standard titration problem that you're gonna see on your exams a lot. So this takes me a minute, and this whole thing gonna take you more than 5 minutes. So 1 minute versus 5 minutes.